Prabha. Digital India. Educated India.
Hello, good morning everyone. Welcome to the class of fluid mechanics. Today we are in the third lecture of fluid kinematics. In the last two lectures, we have already covered topics such as description of fluid motion, acceleration of fluid flow, streamlines, path lines and straight lines, types of fluid motion, vorticity and circulation. So, in today's lecture, we will be able to understand the derivation of the continuity equation and some of the concepts of stream function, velocity potential function, as well as the combination of stream lines and velocity potential lines or equipotential lines, which gives you the flow net. Okay, so looking at the first one, that is the continuity equation. The rate at which the mass flows into the volume minus the rate at which the flow leaves the control volume must be equal to the net rate of change of mass within the control volume. Correct? So that means there is no loss, or the net rate of change is basically equal to what is coming in minus what is going out. So that's how we ensure that the continuity equation is satisfied, or the continuity of the flow or the fluid is satisfied. There is no discontinuity in the whole system. Now, to understand that, let us consider a fluid element. Okay, this is one fluid element, and in this I have the axis which is x, y, and z. X, y are the horizontal axes, and z is the vertical axis. X is positive in the right direction, y is positive this way, and z is positive upwards. Okay, so now we have a fluid element which has dimension of delta x, delta y, and delta z in all three directions. Okay, so now let us look at the flow through these surfaces. Okay, and in this case, the fluid has a density of rho, and the velocity in the x direction is u, in the y direction is v, in the y direction is v, and in the z direction is w. So with this velocities u, v, w, if we look at, let us consider the phase that is perpendicular to the x direction. What is that phase? That is nothing but your delta y, delta z. So this particular phase is nothing but your phase that is perpendicular to the x direction, and let us see how much flow is taking place through this phase. So the mass is nothing but rho multiplied by u is giving you the flux, that is the flow that is coming in, and what is the area? That is nothing but your delta y, delta z. So through this phase, this is the flux that is coming in. Okay? This is the mass that is flowing in through this phase, that is delta y, delta z at this location. Now, at the same time, what is the flow going out along that direction across this phase? So if I want to find it out, then what is the velocity at this particular phase? Because from this point to this point, I have traveled a distance of delta x. All right. So there will be a change in the velocity in the x direction. If the gradient of the velocity is dou u by dou x, okay. So the velocity or the flux that is going to change over this distance is going to be this one. So here it was rho u. Now because of this distance, there is a gradient dou u by dou x. So the flux gradient is going to be dou rho u by dou x, or mass flux that has changed is equals to dou rho u by dou x multiplied by delta x. So now this is passing through the phase delta y, delta z. We could write down this as the mass flux that is going out in the phase this one, and this is the mass flux that is coming in. So now we know what is going out and coming in through this along this x-axis. Similarly, we can find out what are the flow that is passing in other directions. Let us say delta y and delta z. If what I have shown here is delta z, let us say, so that is rho w delta x delta y is coming in, and rho w delta rho w dou rho w by dou z multiplied by delta z is passing through this phase delta x delta y that is here. Okay. Now, if I want to find out what is the net rate of change, so first of all, let us understand what is the change in the x direction. So what is the change in the x direction? The flow that is going out minus that flow that is coming in. So if I calculate that, then what I will get? I will get this term. Okay. I will get this particular term which is given here, isn't it? Or what is the coming flow coming in and minus the flow going out is the flow that is remaining or that is balance within the volume. So inflow minus outflow is going to give you this, that's why you get a minus sign, and that is nothing but dou rho u by dou x multiplied by dou x dou y dou z. Okay. So similarly, if we write down the flux, net flux that is going to remain in all three different directions, we could write down the y direction is going to be this and z direction is going to be this. So finally, this whole combination of all three different directions, we should be able to equate to this one, that is net rate of change of mass within the control volume. So what is that? The mass in the control volume is rho delta x delta y delta z. So delta x delta y delta z is the control volume, and the mass is obtained when you multiply that with rho, volume to density. So change, rate of change is dou by dou t. So dou rho delta x delta y delta z by dou t is nothing but your net rate of change of the mass within the control volume. That when we equated, you can see that in both right side as well as on the left side, you have the volume present in each term. So if you divide by volume all through this equation, what will you get? You will be able to write down dou rho by dou t, which you get it from the right side of this equation here, dou rho by dou t plus, because all these minus will become plus when you take it to one side. So plus dou rho u by dou x plus dou rho v by dou y plus dou rho w by dou z is going to be equals to 0. This equation is nothing but your continuity equation that satisfies the conservation of mass to a control volume. Alright. So now we have seen how to derive the continuity equation. And what is the continuity equation? Continuity equation is a function of time as well as space. You can observe that first you have dou rho by dou t plus, that is the rate of change within time, then dou rho u by dou x plus dou rho v by dou y plus dou rho w by dou z. These are the change, rate of change in the spatial directions. Alright. So this is the complete continuity equation. Now alright. But this equation is in Cartesian coordinates because we have considered x, y and z directions. So this is in Cartesian coordinates. There are other coordinate systems. You may have polar coordinate system, you may have spherical coordinate system. So for different coordinate systems, this equation will change, which we will not talk in this particular lecture or in this course possibly. At later stage when it is required, we will bring it up. Okay. So right now, this is the continuity equation in Cartesian coordinate system. Let us look at how this continuity equation is going to change for different flow conditions. So the continuity equation is given like this. Now, if I say my flow is incompressible, okay. So for an incompressible flow, what is going to change? The moment you say incompressible, what does it mean? That means the flow is not compressible. There is no change in the density of the fluid. So if you say that there is no change in the density, that means rho is constant. Okay. So when rho is constant, the density is constant, you can take it out. And when you take it out, other side is 0, so it will disappear, or it will it will become 0. So rho is going to be 0. So finally you could write down the equation. Okay, so rho is constant, so you could write down the equation as dou u by dou x, dou b by dou y plus dou w by dou z is equal to 0, because the first term dou rho by dou t is going to be 0, because that rho is a constant, derivative of the constant is 0, so that term is going to disappear anyway. So from all other three terms, rho is going to be taken out as a constant, and if you divide that on the right side, it will be 0. So this is what is the equation, simplest equation, dou u by dou x plus dou v by dou y plus dou w by dou z equals to 0. That is for incompressible flows. All right. Now, if I say the flow is steady and compressible, the moment I say incompressible, it is rho is going to be constant, so the equation will be simplified. But if it is compressible but steady, so what will happen? If it is compressible, you cannot take out the rho. Rho is going to be present. But if it is steady, that means there is no change of the flow properties in time. We have already discussed that, isn't it? So if there is no change in the flow property in time, what will happen to the dou rho by dou t term? The derivative of rho is going to be 0. There is no change, so it is 0. So the equation is going to become dou rho u by dou x plus dou rho b by dou y plus dou rho w by dou z equals to 0. So now you know this is the way you can analyze and rewrite your continuity equation, which is applicable for the particular flow condition or particular fluid characteristics. Okay, so if the flow is incompressible, it is this. If the flow is steady and compressible, then this is the equation. Okay, so now let us move to the next concept. So we have already seen the continuity equation. Now let us look at the next concepts of stream function and velocity potential function. So when we look at the stream function and velocity potential function, these functions were initially introduced by Lagrange, and these are denoted as these functions were initially introduced by Lagrange, and these functions are denoted with standard notations. And what are the standard notation? The stream function is denoted with the notation uh, that is psi, and the velocity potential function or the potential function is denoted with the notation phi. So these are standard notations. Usually it is followed. So you should also always prefer to use standard notations. What is the advantage of this stream function and potential functions? If you look at, the advantage is lying in their properties. The psi and phi functions are scalar functions in space and time. So in a flow domain, at every point, the phi or psi function can be defined as a scalar function. So it is not a vector. Okay. So now in a flow domain, if you want to solve something, you need to solve for the velocities in x direction as well as y direction. But same velocity in x and y directions can be denoted with one scalar function, let us say psi. So if I will see that in the next slides, but if I know the value of psi at each point, I can find out what is the velocity in different directions. So that is the advantage. So that's why these functions are very useful at some points. The other characteristic, other property of these phi and psi functions are given here. So you have the psi and phi functions. These functions should satisfy the continuity equation for the flow to exist. If you cannot satisfy the continuity equation using the phi function or even the psi function, then the flow, the function that you have defined cannot really show a flow, or the flow is not going to exist for that function which has been defined. Okay, so flow to exist for a psi function or phi function, it has to satisfy the continuity equation. The mass has to be conserved, right? So let us look at various aspects of velocity potential function first. So velocity potential function phi is a scalar function in space and time. The gradient of this phi function in any direction gives the flow velocity in that direction. Okay, if you take the gradient of the phi function in any direction, that is any spatial direction, if you take dou phi by dou x, it should give the velocity in x direction. If you take dou phi by dou y, it should give the velocity in the y direction. All right. So now let us write it down. If I write dou phi by dou x is going to give me u, dou phi by dou y is going to give me v, dou phi by dou z is going to give me w. All right. So now you will ask me, why do you have a minus sign here? Now let me take you from the practical aspect to the other side. Now practically we know there is a flow, there is a velocity. Is going to happen from what, where to where? It is going to happen from higher potential to lower potential. If you have higher mass of water here, I will say it is a higher potential, and there is a lower level of water here, there is a lower potential. So the flow is going to take place from higher potential to lower potential. Now if I take the gradient, gradient is my phi 2 minus phi 1. So if I look at phi 2 is smaller, phi 1 is larger, then I'll get a negative value. So when I derive the velocity, I'll get a negative value if I have not considered that. Then whatever I get, I will have to always write that the flow is going to take place from higher potential to lower potential. So instead of writing that always, we can incorporate that negative sign here in the expression itself. So we get a positive value and we continue as usual as per our analysis without every time writing higher potential to lower potential. So to give you slightly more detailed example, let us look at, you have, let us say, the direction x-axis to which the flow is taking place, let us say, and the flow is taking place from in the x-axis, the x direction. Okay, so if it is taking place in the x direction, I will tell that my value of phi is phi 1 is some value at this point, and I have, let us say, another point where it is phi 2. Okay, so my direction of x is positive in this direction. All right, so now this is my phi 1 and phi 2. I have assumed x as my positive direction, what I have shown here in this figure. Now I have two values of phi 1 and phi 2. If I want to find out the term dou phi by dou x, then what it will be? It will be phi 2 minus phi 1 divided by delta x. Okay, so delta x is nothing but the distance between these two locations. Okay, this is nothing but my delta x. So if I calculate now phi 2 minus phi 1 divided by delta x, I'll get a value which will come out as positive. Okay, because phi 2 is greater, phi 1 is smaller, divided by delta x is going to give you a positive value. See, the flow is taking place in this direction because this is a higher potential, this is lower potential, but still I am getting a velocity which is positive, but my x direction is positive rightwards. So it is contradicting. I cannot write a positive value when my standard notation of x is positive rightwards, right? And again, if I say velocity is positive, that is implicitly telling me that the velocity is in the positive direction of x, but it is not. It is in the opposite direction. So for a standard notation, if I have already the minus sign implicitly in that, then the minus sign is going to come here. So this automatically will come as a negative velocity. Okay, then it will directly tell me that the velocity what is going to exist is in the negative x direction, and which is correct. Okay, that's why you have the negative sign here. All right, so we have these three different expressions One is for u, that is minus dou phi by dou x, then for v, that is minus dou phi by dou y, then for w, minus dou phi by dou z. So if you take the negative gradient in any direction, that gives you the fluid velocity in that direction. Okay, so phi function is a scalar function in space and time whose negative gradient in any direction gives the fluid velocity in that direction. Got it? All right. Now let us look at what is going to happen for different types of flows. What will, whether the velocity potential phi will exist for irrotational flows, or it will exist for rotational flows, or what will happen? The velocity function phi or velocity potential phi will exist only if the flow is irrotational. Okay, so that's the characteristic of the, or the property of this phi function. Now that means I should be able to satisfy the irrotationality or irrotational condition using the phi function. So what is the rotation? First of all, let us write down the equation for rotation. We have already derived. So if I have this axis x and y, and I want to write down the rotation about this, that is going to be my omega z. About the z axis, this rotation will be obtained. So if I write down, let us say omega x, so that is okay. So if we are talking about omega x, then the rotation is about, rotation is in the plane of y and z axis. All right. So the expression for omega x is going to be 1 by 2 multiplied by dou w by dou y minus dou v by dou z. Okay. So now let us substitute the values of w and v in this case. So if you substitute the value of w, what will happen? You will write down as dou phi dou by dou y multiplied by minus dou phi by dou z minus dou by dou z multiplied by minus dou phi by dou y. So if you see this expression, you have dou square phi by dou y dou z minus dou square phi by dou y dou z. So both will vanish, and finally you are going to get the equation 0. So by substituting the values of u, v and w, you should be able to derive the irrotational, or you should be able to evaluate the rotations, and if that goes to 0, if wx, wy and wz all are equal to 0, then you can say that the phi function satisfies the irrotationality and it is going to exist, or it is correct. Okay, so phi function has to satisfy the irrotational condition, and phi function will exist only for irrotational flows. Okay, so yeah, this is what we have already seen. Now let us see what are the other properties or other characteristic of the velocity potential function. If a velocity potential function satisfies the Laplace equation, then also we can tell that the flow is incompressible. Okay, we have already seen that if it satisfies the irrotationality condition, we can find out the value of omega x, omega y, omega z, and tell that okay, this is irrotational. But at the same time, if the velocity potential function, that is phi function, satisfies the Laplace equation, then also we can tell the flow is incompressible. So what is Laplace equation? If we substitute, let us say this is our continuity equation. So continuity equation for incompressible flow, which we have already seen. Okay. So now in this continuity equation, if I substitute the expressions for u, v and w in terms of phi, so what are those? Those are u is equals to minus dou phi by dou x, v is equals to minus dou phi by dou y, w is equals to minus dou phi by dou z. If I substitute that, I can write down minus dou square phi by dou x square minus dou phi square by dou y square minus dou phi square by dou square phi by dou z square. So here dou square phi by dou x square, dou square phi by dou y square, dou square phi by dou z square will give rise to 0. Okay, so if I take the minus common, I can write down this expression. This expression is nothing but the Laplace equation, which I can write down in vectorial form. It is dou square, dou is the del is the operator, right? So del square phi is equals to 0, which is nothing but your Laplace equation, isn't it? So this del square phi has to be 0 for the flow to be incompressible. Okay, so you should be able to check it and find it out. Now, if this phi function, which is a function of both x and y, we have seen that in a domain, let us say I have the 2D domain, that is x and y plane. Okay, in that x and y plane, phi is a function of x as well as y. And if this phi xy is constant, this is going to represent one equipotential line. That means if my function, which is phi xy, is let's say x square plus y square plus 2xy plus 3x square y or something, so that's a function. If that function is equals to some constant, that constant will give me one line. That is nothing but my equipotential line. Means what? Means the potential phi value is going to be same along that line anywhere. So if I calculate the gradient along the equipotential line, I will get a value that is going to be 0, because equipotential everywhere it is same, so there is no change. So my gradient is going to be 0. All right. Now let us move to the next function, that is our stream function. All right. So when we are talking about stream function, there are some basic properties we should first understand. The stream function works only if it is defined for two terms or mainly in 2D. Okay, so it works only if the continuity equation is reduced to two terms. And when it can be reduced to two terms, if we have already seen, if we have the continuity equation for incompressible flows, right, then the equation becomes dou u by dou x plus dou v by dou y plus dou w by dou z. So there are three terms. Now, if I reduced one dimension, I take only in 2D, then it will become two terms. So this stream function, when the flow is steady, incompressible, and 2D, two-dimensional, then the continuity equation can become or reduce to two terms. That will be dou u by dou x plus, let us say, dou v by dou y. I have only xy plane, let us say. All right. So dou u by dou x plus dou v by dou y will be equal to 0. This is the continuity equation which you need to satisfy for stream function, or stream function has to satisfy this equation. It can only be applicable for 2D flow problems. All right. So now let us define what is this psi function or stream function. The stream function is a scalar function in space and time, and space means 2D, x and y. Okay. So stream function is a scalar function in space and time whose gradient in any direction gives the fluid velocity perpendicular to that direction. So the gradient of psi function in any direction gives the velocity perpendicular to that direction. All right. In phi function, the gradient or the negative gradient in any direction was giving the flow velocity in that direction. Whereas in case of psi function, the gradient in any direction gives the velocity perpendicular to that direction. Okay. So now you can see that we have written u is equals to dou psi by dou y. So if you take the gradient in y direction, you will get gradient in y direction, you will get the velocity in the x direction. If you take dou psi by dou x, that is the gradient in x direction, will give you the velocity in y direction. All right. So this is satisfied. But now you will ask me, what is this minus sign here doing again? And that too, here it is not there. Only in this case it is there. So why this minus sign is required? This is required to satisfy the continuity equation. If you look at this continuity equation here, this is dou u by dou x, and you substitute, let us say, u here. So u is nothing but dou psi by dou y. So it will become dou square psi by dou x dou y. And if you substitute v in this, so it will become again dou square psi by dou x dou y with a minus sign. If you don't have the minus sign, this is not going to be 0. So to satisfy that, you need a minus sign. Okay. So you can take the minus sign either in terms in u or in v, doesn't matter. both will give you the same, but you have to be consistent throughout whatever you are analyzing, you are doing. It is always better to be consistent in standard notations or standard uh, uh, practice. So in this case, let us say we have considered u equals to dou u dou phi by dou y. Sorry, u is equals to dou psi by dou y, and v is equals to minus dou psi by dou x. This will continue throughout. All right. So this minus sign has come in to satisfy the continuity equation. All right. Now that I have shown here, so if you substitute the values, you will get a output as 0. Okay. So there are certain properties of psi function. What are those properties? When psi function satisfies the continuity equation, it indicates that flow exists. Or if I want to find out whether the flow exists or not, then I have to check whether my psi function is satisfying the continuity equation or not. So psi function exists when it satisfies the continuity equation. Okay. However, it is only satisfying the continuity equation. That means the flow exists, and we know that the flow can be rotational or irrotational. So phi function can exist for a rotational flow as well as for a irrotational flow. Okay. So phi function we have already seen, phi function will exist only when the flow is irrotational, whereas psi function will exist when the flow is rotational or irrotational. So if the psi function satisfies the Laplace equation, then the flow is going to be irrotational. Okay. We have already seen the Laplace equation. That is nothing but dou square by dou x square plus dou square by dou y square plus dou square by dou z square. In this case, it is only 2D. So dou square by dou x square plus dou square by dou y square operated on something. So that is operated on psi here. So I'll be able to write del square psi is equals to 0.